Oh. Okay, let's start then, so we can finish early as well. So, what are your answers? Has anybody got question 1?
22 items a month.
22.
No, 22 every 3 quarters.
Okay, I don't have 22. Got 55. 54.7. That's about 55. Okay, let's have a look. Let's see what it is. Okay, so am I in the right area? Okay, so the formula for the optimal order quantity was 2dk divided by h, which doesn't tell you much if you don't know what dk and h are, right? So d is the demand, so that was 30 units per month. H was the stock holding cost, storage cost, if you like. And C you don't need for the formula. So K is £15 ordering cost. Okay, so when we plug it into this, 2 times 30 times 15 divided by 0.3, root of that, that's 900 divided by 0.3, so that's 3,000, square root of 3,000. So 50 squared is 2,500, 60 squared is 3,600. So the root of 3,000 is something between 50 and 60. So I trust your answer that it's 55, about. I'll do about 55. Which means that, okay, so what does 55 say? Pardon?
Every 1.81.
Yes, you're one question ahead. What's the meaning of 55? 55 items in every order. Okay, so every order should be 55 items, and therefore the time is, well, because you need 30 per month, and it's not ordering. I've missed my own question. So it's asking about producing a batch of these items rather than ordering them. But the principle, the mathematical model is the same. Okay, so whether you're ordering them from an external supplier or whether you're ordering them from someone who can make a batch within your own company, that doesn't make any difference. So every order should be 55 items. So the time between two orders, any two consecutive orders is, well, we're ordering 55, we need 30 per month, so that's about 1.83, you said? Months or something like that? Okay, excellent. Has anybody done question 2? What are your results?
Individual, I got 45,977 pounds.
Individual. Can you confirm it?
I was got the answer.
Okay, so individuals, you got 46,000 pounds approximately. Okay. Approximately. I can't remember the answer, so I'll put it here. I'll check it afterwards. Has anybody else got 46 or something else? 46? Excellent. So I take it to be correct. And then what was the best group replacement?
Every 4 months.
Is that the same?
40,500.
Sorry, 50?
40,500.
4,500. That's group. This is not how you spell group with the blow. Group replacement every 4 months. And you get 40,500. So we take this as the recommendation to the managers that they should do a group replacement every 4 months, and the average monthly cost is going to be 40,500. Very well done, thank you. So now you can mark yourselves and put the number of marks on the register as usual. That's it. Yeah, same time. Hand up. Any questions about this? Or anything else, really? Good. Today is a big day because today we're going to finish spreadsheeting. Well, the spreadsheet model. We'll do a bit more spreadsheeting afterwards as well. But this chapter of or topic of spreadsheet models will be finished today, and we'll move on to linear programming models, which some of you know from Decision in college or in secondary school. Some of you don't know, so we'll try to bring everybody to the same state of knowledge. But before we do, we still have one spreadsheet model to finish, and that's depot locating. Oh, and also what's going to happen is that in the coming 4 weeks, from next week on, for 4 weeks, Philip will have these 2 hour slots, and I will be doing the 1 o'clock 1 hour lectures. So you will have less of me, which is always a good thing. What is depot location? Okay, so you can see it here. You can also, if you've got the handout already, you can see it there. The question is this. We have a small delivery company, say, okay? And that delivery company is taking flour from a mill, and it's delivering this flour to some bakers. But what we don't want to do is take the flour directly from the mill to the bakers, because there's just not enough flexibility at the mill. Okay, so what we want to do is send large trucks to the mill, bring it to a little warehouse where we're going to store it for a bit, and then from that warehouse, in small vans, we're going to take the flour to the individual bakers. Okay? Now, the question is, where would we best situate our warehouse in the area? Okay. Does that make sense? And what? Now, the model that we'll be looking at for positioning the warehouse comes from, it's a kind of a simple model. So, the data we have are the coordinates in kilometers of each of the 7 bakeries, and also the coordinates of the mill. And then we also have number of vans per week that we need to send to each of the customers, each of the bakeries. So this is what we have. And we are assuming in this model that we can build the warehouse anywhere we want for a plane, a Euclidean plane. So what we're looking for is the coordinates of the warehouse where we, the coordinates in the plane where we want to build our warehouse in order to minimize the transportation costs. Okay, question clear? So the first thing we can do, I want to do, is to visualize. Now, the picture is not great, I give you that, but I also admit that I made the picture. One problem with the picture is that you don't know what the customers are and what the mill is. Okay, so the mill is this. Does it show as red? So now, what do we want? Where would you build the mill? Here? Probably not. There? Probably not. So you want to build it somewhere. Thereabouts. But we don't know where exactly. Okay. I'm a bit confused today. So what am I doing? I didn't say what the okay. So the little discs there. The individual, one of them is the mill, and the rest of them are the individual bakers. And the size of each of the discs corresponds to the demand in number of vehicles of each of the bakers. Okay. So this is what the map represents. Now, what we're going to do in this model is we need to look at the distances of this point from all the customers and the mill on this. Now, what do we want to minimize? Is there something to minimize? So you want to minimize the distance between the bakeries and the warehouse. Well, but which one? Any single one? Or do you want to minimize the sum of all of it? Okay, but do you want to minimize the sum of all the distances? Or do you want to minimize the weighted sum of all the differences? What is the weighted sum? Yes, so here we have a customer. Let's try to identify them in here, in the table. So in the table, there is what are the coordinates of that guy? It's about 190, 170 or something like that. So it's going to be number 5. And that bakery requires 14 vehicle loads per week. Okay? Whereas this one, which is coordinates about 30 something, 120 something. So which one is that? It's probably number 4. That requires 41 vehicles per week. Okay. So each of these bakeries have a different demand per week. So this one should have a higher weight, obviously, because you're sending 41 vehicles there every week, whereas this one you're only sending 14. Okay? Oh. Did I catch them? Also, we'll be going quite often to the mill, but the mill it's cheaper. It only costs. It says there it only costs £1.20 per kilometre in vehicle load to get it from the mill, because we're taking a larger vehicle that's cheap to run. Whereas to the customers it costs £2.10 per vehicle kilometre to get it there. So we want to take care of that as well. So that's what we're going to do. Okay, so now stop disappearing. Stop disappearing. So our objective is to minimize the total cost rather than the distance in this case. So the total cost, we can separate it into 2 components, because one of the components will be doing business with the mill, and the other components will be delivering to the bakeries. Okay, so so the total cost is equal to the sum of the local delivery cost and the trunking cost. Okay, the trunking cost is a technical term for the cost of delivering large batches of stuff from a home cloud, from somewhere big to your warehouse. Whereas the local delivery cost, that is self-explanatory. That means that you're delivering locally to small customers. Okay. Okay, so what is the local delivery cost? Okay, the first thing we observe is that we have 7 different customers. Okay, so we call the customers 1 to 7, and we'll have to add the cost for each individual customer all together. So K goes from 1 to 7. Now let's say that the demand of customer K is QK. In vehicle loads of customer K. Then we need to multiply it by the £2.10. Okay, so the £2.10 is the cost of the local delivery per vehicle and kilometer. So I'll call it CLD. So CLD equals £2.1, which is so these are the unit delivery cost. This is the unit delivery cost. Okay. And okay, and then we have to multiply it by the distance we travel. So okay, the distance of the warehouse and customer K. Okay, so it's all starting to be a bit confusing. It's confusing me anyway. Okay, so so where do we build the warehouse? Aha, we don't know. The answer will surprise you. At coordinates x, y. Did you expect that? So what are x, y? Stop sleeping. What are x, y? Don't say coordinates. I know that. I've just written that.
That's possible solution.
All possible solutions. Sorry? The best. It will be in the end when we get there. But what are these things called that we try to find the best value of? They're called something variables. What variables? Ah, yes, decision variables. So x and y will be our decision variables. Well, they're called decision variables because we want to make a decision what they will be. Okay? This is the whole point of this model, is to decide where else should we go. So we've got these two decision variables, x and y, and we want to determine the best possible value. And those are the only decision variables, in fact, in this model, because we are only looking at where to build the warehouse and nothing else. Everything else is determined. So we've got this. Okay, so now let's say that the coordinate of bakery K are xk, yk, and of the mill, the x, n, y, n. That's the show? Okay, so what is the distance? Now, what is the distance between the warehouse and bakery K? The question seems simple enough. Okay, so I've got this warehouse. Its coordinates are x, y. I have this bakery, and its coordinates are xk, yk. What is the distance of these 2 points?
Square root of xk minus k squared plus yk minus y squared. So Pythagoras.
Do you agree? Excellent. So when I do the Pythagoras, actually here, so this is a right angled triangle. This side has length xk minus x, and this side has length yk minus capital Y. Okay, so the distance of the point xy and xk, yk is the square root of x minus xk squared plus y minus no yk squared. Have I done it wrong? I was expecting someone to point out that I did it wrong. Yes, and there we go. Okay, so xk minus x, and here I wrote x minus xk.
We would make that a vector because even if it becomes a negative value, we square it if it get a positive value anyway, then add them together and square it. So
Exactly. But I felt the need to clarify based on my past experience. I got somebody who would say, no, it's gone. Okay, so it doesn't matter which way you write the difference there, because then whether it's negative or positive, when you square it, it becomes positive anyway. Okay, so the order in the subtraction doesn't matter here. So this is it. Now, however, what we're going to do is we're going to add something that's called a wiggle factor. So the distance we've established that the distance of xy, that's the warehouse, and customer k is given by Pythagoras, but what we're going to do is put some alpha here times the square root of xk minus x squared plus yk minus y squared. I've probably changed the order again, but as we've already clarified, it doesn't matter. Okay, so this alpha is called the wiggle factor. That's a technical term, isn't it? And so this is supposed to compensate for the fact that roads are actually not straight lines, so roads wiggle. Okay. So road because roads are not straight. This kind of alpha, you somehow determine based on experience how much it should be, depending on what area of the world you're operating in, and you set it to something. So we can, for us, then to actually calculate the solution, let's take alpha. Need to look in my notes for that. 1.15. That's not something that you can, it really just, it depends on the particular situation that you're in. You can guess. You can approximate the distances on the road. What's that noise? It's the speakers. Do we have everything? Yeah, almost. We don't have the. Where are my keys on the floor? Someone's been messing with my keys. Yes, so we kind of have everything when it comes to the local delivery cost. So the trunking cost is just going to be well, it's just going to be okay. What was the? So I've moved it too far down. Yes, so it's going to be the amount transported times the cost of the trunking times the distance of the warehouse from the mill. Okay, that is quite good. So we know that the CT CT is £1.20. That's somewhere in the data we had. Yes. Now, why did I leave the space here? You don't know? I think you do. Does anybody else know?
Is it not
Alpha. Could be the alpha, but no, I put the alpha here into the distance formula, so I don't need to do the alpha. Okay, so I'm confused you because I have two different formulas for the distance. But this one doesn't count. That's just on a piece of paper. I'm going to throw it to the bin to finish here. But no, but this I'm not. But this one counts. Okay, so this is the distance. So the alpha is already there. That's already part of this distance. Okay, so the dist doesn't give you the straight line distance in this case. It gives you the wiggle distance. However, when you compare it to what we had up here, we had the distance, okay, the distance there, we had the unit cost of local delivery, okay, then we have the unit cost of company delivery, but we had the quantity, how many vehicles the customer wanted. So we should put some quantity here as well, because otherwise we would just have it one vehicle, and we're doing more than one vehicle. So what is the quantity? The total demand. That's a good suggestion. So how do we find out what that is? There are some smart people in the audience. Yes, we add the demand of all the customers together from 1 to 7. She got offended. I get the sack tomorrow. Well, Philip can do linear programming as well, so someone will take care of these lectures. Right. So let's put it all together. So what do we have? We have the decision variables. Are x and y, which are the coordinates of the warehouse that we want to build. The objective is to minimize the total cost, which is the local delivery cost plus the trunking cost. Okay, so the formulas are there somewhere. The trunking cost is still visible. The other formula is hidden somewhere. And then we should also have constraints, usually. So what are the constraints?
The infrastructure can withstand the number of vehicles. 41.
Can you write it as a formula? No, that's more what we would call an assumption. No, I'm asking about constraints. Those are this must be less than that, and this must be bigger than that, and this must be something. Yeah.
None of the values can be less than 2.
That is a fairly typical constraint that appears in many problems. Okay, yes, that's true. That's a very good guess, in fact. But here, I don't think we need that because probably don't need that because if we build the warehouse to the left of that straight line and the axis, then it doesn't really matter, does it? So we don't really need a constraint that tells us that the coordinates must be greater than or equal to 0. So there are basically no constraints in this model. Okay, so well, I'll say that both x and y are some real numbers, and that will be our constraint. I think. So this is our model. Are there any questions about this model? No? Now, we still need to solve the model, but let's first do a 10-minute break, and then I'll show you how this model is solved. Just to do anything at all. Okay. If you don't complain, if you don't hear about me, you can go. Has everyone signed in? Good. Okay then, how do we solve the model? How do we solve the model? Any guesses how we solve the model? Spreadsheet, yes. I've got one here, look. That's all. Okay. So what does the spreadsheet do? Okay, we've got the decision variables here in yellow. Those are the coordinates of the warehouse. It's got deco here. All the data are in gray. So the X and Y coordinates of all the customers, the X and Y coordinates of the milk, the total, okay, so the queues, the demands of the individual customers. Now, when you look at this queue, Okay, it doesn't show the formula in a very large letters, but you can see that that's just the sum of all these demands as we have in the formula there. And then the parameters that give you the price are there. Okay, so what are the good principles of spreadsheeting? All the data that we're using should be somewhere in a cell. Okay, so you see everything is there. All the coordinates, all the demands, all the delivery costs, all the wiggle factors, they're displayed somewhere. And nothing is hidden in the formula. What you could do is put the wiggle factor, 1.15, 1.15, into all the delivery costs, or into all the distances, or something like that. But you don't do that because you want everything to be visible. But when you change it a little bit, you don't want to be changing all the formulas. Okay? So the formulas stay as they are. That's the thing. Now, distance is somehow calculated, the cost is somehow calculated using those formulas that we had. And the thing is, when I change the coordinates, so when I look at there, and I want that. So when I look at the map, okay, this was my guess, the dot here. So I put the dot there. It's about 100. Y is also about 100. So when I put 100, 100 as my coordinates, everything recalculates and it gives me 96,706 pounds cost. Okay. If I want, I can try 200, 250. And the cost is much larger. Okay. So also, if I change the wiggle, then it's going to change things. But I don't want to change the wiggle. I just want to find the best coordinates of the warehouse. So now, of course, I could play around with trying different 115, 104, and trying to get as small a number in the total cost as I can. But there is a smarter way. I'll show you. And the smarter way is called the solver extension of Excel. Has anybody ever seen the solver extension before? You have? Of course you have. Anybody else? Yeah? So there's nothing new for you here. Why do you even keep coming? Oh no, stay. Okay, so the solver is when you click on data here, there's a solver down there. Exactly where the mouse is pointing. Okay, there. Except the first time you log into the computer and run Excel, it's not there. So what you have to do is, now watch. Click on File, Options. Here the second last thing is called Add-ins. And there at the bottom it says Manage Excel Add-ins. So you click on Go, tick Solver, and OK it. Okay, it thinks for a bit, and then it adds Solver up there where I promised it would be. You'll have a chance in the lab. Okay. Now, I can see it's already been pre-filled for me. So obviously someone in this spreadsheet has been using Solver before. Okay, so what there is the objective. That's probably too small for you lot to read, but it says cost. Instead of cost, it could just say B3. Okay, but it says cost because when I click on the cost, see, I give it a name which is cost. So the thing is, you can select things in the spreadsheet and call them something. So you select 2 cells and you give them a name, and Excel remembers the name you've given them, but you don't have to. You can use a solver even without that. These 2 cells that are changing, the coordinates, I call them cohorts. So when I look at the solver, I want to set the objective to be cost. I want to minimize it by changing the cohorts. There are no constraints. Here in this box, it says that I don't, that there should be non-negative. I don't need them to be non-negative. Now I have to select the solver. Okay, so it gives you 3 options: non-linear, GRG non-linear. It gives you simplex LP and evolutionary. Now, this problem, for reasons that I don't want to explain, you have to select non-linear because it's not linear. And we'll see in a couple of minutes what it means to be linear. So yeah, but this one's not linear, I promise you. So you can't use simplex LP, which is linear. And evolutionary is an overkill for this problem, so you don't want that either. Okay, and you click solve. And solver solves, and it comes up with a solution. About 88, 171, something like that. And these are the coordinates that Excel thinks lead to the minimum cost of £93,664 a week or so. Yeah. So this is how it works, and we'll practice it in my lab. I don't know what Philip's going to do, but we should practice this. So if you come to my labs, I will show you how to add solver, and then you'll be able to do it on your own and set up your own spreadsheet and solve everything, I promise you. Any questions? So that means we've finished spreadsheeting. That means we're starting linear programming. And that's a very exciting topic. Use the job. Okay, so before we start linear programming, who wants the slides to be here on the left? Who wants them to be there on the right? Who wants both? I think the left is winning. But it costs me nothing, so I'll put them to both. Have you read it? While I was chatting away about nonsense. This is supposed to be a big promotion for linear programming, because linear programming is big. Everything is linear programming. If you can't solve problems using linear programming, then you're in trouble. Okay, I don't think I've quite succeeded in and then how big it is in this slide. Yeah. Okay, so the I've only put the two main reasons why it's such an important topic in operational research. And the first one is that many problems are amenable to linear programming. Many problems you can actually model as linear programming problems. So it's very useful in this sense. And the second reason, it's a combination of the two really. So the second part of the reason is that it can be solved quite efficiently and quickly, even for large-scale linear programs where you've got hundreds of thousands of decision variables and hundreds of thousands of constraints. You can still run it relatively quickly and get your solutions in reasonable time. So for the combination of these two reasons, it's a very important technique in operational research, and that's what we'll be learning for, well, many weeks now. And today, let's just start with an example. And the example is silly, but it's supposed to be entertaining. Okay, so there are 168 hours in a week. I don't know how I came up with this figure. It's probably 7 times 24. Okay, yes. And a student wants to determine how many of these hours they want to spend studying, how many hours they want to spend partying, and how many hours they want to spend doing everything else. Okay, that's a very common, well, it used to be when I was a student, that was a very common problem for students to decide how many hours to spend doing. Okay, and there are some constraints. So I can't remember what I put there. No, oh. I've lost the solution. Okay, never mind. I won't give you the solution. No, it was here somewhere. Please come back. Anyway, let's go through the. Okay, so if you do too much studying and partying and nothing else, that will kill you. Okay, that's one of the constraints of this problem. So you have to spend at least some minimum amount of time on everything else. And research in the United States, which I think also applies in this country, has established that the minimum number of hours per week that a student has to spend doing everything else, not to be killed, is 56 hours. Okay? So that's a constraint. Also, too much studying is not good for your mental health. Research in Germany, but I think it applies in this country as well, has established that partying and everything else has to add to at least 70 hours per week. Okay, so that's a constraint. But also research in this country at this university has established that spending less than 60 hours per week studying is guaranteed for you to not pass the exams. Okay, so there's a constraint that says that studying has to be at least 60. Can you see the constraint? Okay, now this is a slightly intricate constraint. Okay, but now you have all the constraints. So this one is kind of a relationship between studying and everything else, and partying. So partying kind of takes away from everything because it's you know, you get drunk and that's not good and so on. But yeah. Now you've got the constraints. So, okay, so what are the constraints? We want to find okay, so we want to find real numbers S, E, and P. So S, E, and P are your decision variables, okay? And which satisfy the following. Okay, so the first constraint was E is greater than or equal to 56. Then we had P plus E is greater than or equal to 70. Then we had S is greater than or equal to 60. And we had 2S plus E minus 3P is greater than or equal to 150. Okay, we also had a constraint. We also had a constraint that says that when we add them all together, we get the 168 hours of the week. And we also need to make sure that we don't get a nonsensical answer by getting a negative number of hours to spend partying, which we can't do, obviously. Okay. Try to find such numbers. I'll try to find such numbers as well, but I'll cheat. I found them. Found any? Or is it too hard? Who's still looking? Do you want more time? Or do you want me to give you some? Give you? Just you or everyone? Okay, I have found some of these numbers. So yes, for example, I found you can spend 80 hours studying and 20 hours partying and 68 hours doing everything else, apparently. So does it all work? Okay, so E is 68, so this is satisfied. B plus E is 88, so the second constraint is satisfied. S is 80, so the third constraint is satisfied. Now this one, 160, 228 minus 60 is 168. So that's satisfied. They add to 168. B is non-negative. Yeah. This is what's called a feasible solution. Okay. So now, I think everybody agrees that partying is twice as good as everything else, and studying is none good at all, which gives us the objective function that says that you should maximize 2p plus e, the value of this expression. Okay. And to find the maximum is your homework. Now, the problem with the homework is the following. The problem with the homework is that when I was writing it, I forgot to put p greater than or equal to 0. However, I probably didn't have to do it because p has the largest coefficient in the objective function. So so it's very likely to be positive in the optimal solution. Doesn't matter if you don't. If you don't know what I'm talking about, that's good, because we'll be learning all these things and you will know very well what I'm talking about before December. Okay, so your homework is this, and to find the optimal solution there, or to find as large as you can get to p plus e. If you know sophisticated methods, you can use sophisticated methods, but you don't have to use sophisticated methods. It's okay. And the second homework problem is a bit of a logical puzzle, so that's something for you to have fun with. And like, I'm very efficient in these lectures, it turns out. So I have a plan for 2 hours and I cover it in like 1.5 hours. So that's good for me because I can go home early. But yeah, we'll start next week. And remember, in the early lectures, by looking at this somewhat more practical problem. Thank you very much. Enjoy the rest of your week. See you in the labs. Don't complain about me.